Bismillahir Rahmanir Rahim. In our last lesson, we discussed about the two source interference. And two source interference means there were two waves coming from two different sources. They were meeting at a point, and in some areas they were constructively interfering, and in some areas they were destructively interfering. We discussed the two necessary conditions for constructive and destructive interference. This was the formula, this was the necessary condition for constructive interference to happen. That means the path difference, delta S, between any two waves, if the path difference is 0 lambda, that means 0 times the wavelength, or the path difference was 1 lambda, that means 1 times of wavelength, or the path difference was 2 lambda, that means 2 times of wavelength. In such a scenario, the constructive interference took place. And if it was half an integer, for example, 0.5 of a lambda, or 1.5 of lambda, or 2.5 of lambda, in such situations, the destructive interference took place. That means one crest was falling on another trough of another wave. That way, when the waves got added together, their displacements got cancelled out. I ended our previous class on a note that if the two sources are vibrating 180-degree out of phase, that means if the source S1 was creating a crest at the moment when S2 was creating a trough, dotted line indicates a trough, these sources are said to be vibrating out of phase or 180-degree out of phase. That means when this wave will be creating another crest, the other source will be creating another trough at that same point. So that means when there were two crests, something in between them was going to be a trough. Whereas it's the opposite for the source S2. Whenever there are two troughs, there's going to be a crest at its center. So such a movement, when one wave is creating one source is creating a crest and the other one is creating a trough, such a scenario is said to be, the sources are said to be 180-degree out of phase. So in this case, the formulas that I told you, they will now get interchanged. We don't need to go through the entire process. I will just show you one calculation just so that you know how are the formulas going to get interchanged. Okay. Here, for this point only, this is the one that I'm going to show you. We can see that here there is a bold line from S1 and there is a dotted line from S2. This is indicating that at this point there will be a destructive interference. Destructive interference. Let's perform some calculations to prove that. Path difference helps us to understand if there's going to be a constructive or a destructive interference. We can see from S1, this is one wavelength, and this is going to be another wavelength. Two wavelengths. So from S1, let's call this point to be P. From S1 till P, you subtract that with S2P, do you get 2 lambda minus 2 lambda as well? That means the wave that was coming from S2, it traveled one wavelength this way and another wavelength this way. So two wavelengths were traveled by S1 till P and from S2 till P. So in this case, the path difference comes out to be 0 lambda. If you remember in the previous case that we discussed, if the path difference was 0 lambda, it used to be constructive interference. If not, we'll go back and I'll show you. You can see here, when at point B, the path difference was 0 lambda, it was constructive interference. Right? At the point B, where the path difference from both the sources was equal, the answer was 0, path difference was 0. In such a scenario, when the path difference used to be 0 lambda, it used to be constructive interference. But that happens only if the sources are vibrating in phase. You can see the first line for both of them that I drew, this one and this one, they are both bold lines. But in case if the sources vibrate 180-degree out of phase, you can see that here this one is a bold line and this one is a dotted line indicating that they're vibrating 180-degree out of phase. So in such a case, if the path difference is equal to 0 lambda or 1 lambda or 2 lambda or 3 lambda, the path difference is going to show us destructive interference. Destructive interference. So if the sources are in phase, the integer multiple of wavelength shows constructive interference. But if the sources are 180-degree out of phase, the path difference shows us destructive interference. So there are two formulas which we have already discussed. Delta S is equal to n lambda and delta S is equals to 2n plus 1 into lambda by 2. If sources are in phase, if the sources are in phase, this formula will show us constructive interference and this formula will show us destructive interference. But if sources are 180 degrees out of phase, this formula will show us destructive interference and this will show us constructive interference. Examiner will tell you if the sources are in phase or if the sources are 180-degree out of phase. Most commonly, the questions are designed in such a way that sources vibrate in phase instead of 180-degree out of phase. Around 90% of the time, this scenario is going to be applicable. Sometimes examiner might say the sources are 180-degree out of phase. In that case, you'll be using this formula for destructive and this for constructive. Okay. Do you have any questions so far?
No.
All right, that's great. I'm going to show you Young's double slit experiment. Young's double slit experiment. Before that, I would like to recall for you diffraction. Diffraction comes from O level. This is a physical phenomena. We don't know why it happens, but it's a physical phenomena that we have seen to be happening. If we need to define for 1 mark, we will say it is the spreading of a wave as it passes through an aperture. Aperture is an opening. Or I can write another definition for it, that is bending of a wave around an obstacle. There's a necessary condition for diffraction. Note, maximum diffraction happens, maximum diffraction takes place if the wavelength of the wave is comparable to the size of the aperture. I'm going to recall a diagram from O level. If you remember, we used to represent a wave by using wave fronts. These parallel lines, they are indicating a gap of 1 wavelength, and this perpendicular arrow that I am trying to draw here, this one, is showing us the direction of the wave. This arrow, which is perpendicular to the wave fronts, is showing us the direction of the wave. Direction of wave. So when this wave passes through a cardboard that has a small hole in it, the aperture, these wave fronts, they are going to become curved. The gap between these wavefronts is supposed to remain the same. So I just realized my mistake that I drew them a little closer. So I'm going to redraw them. The gap between them should remain the same. See, if this was 2 centimeter, then these should also have a gap of 2 centimeter. Wave that was traveling towards the right, after passing through the aperture, that same wave is going to travel in all possible directions like this. But this wavelength is supposed to be comparable to the size of an aperture. Comparable means approximately equal. Doesn't necessarily have to be equal, but it has to be approximately equal. But what if I force these waves to travel through a cardboard that has a bigger aperture in it? You can see the size of the aperture is bigger. In this case, the wave fronts are going to be less circular, and they're going to be more rectangular like this. This is indicating a smaller spreading out or a smaller diffraction. Most of the waves are traveling still straight, only a little part of them is bending. This portion is curved, this portion is curved. Whereas for the previous diagram, the entire wavefront got curved. So in this case, there is more diffraction, and in this case, there is less diffraction. Diffraction is something that is common with all types of waves. Note, I'm going to write this fact as a note. All waves will diffract. In fact, diffraction is such a common trait for all waves that we use diffraction of a wave to identify if something is a wave or not. Okay. Imagine I discover an unknown entity in the world and we don't know if that entity is a wave or a particle. We don't know that. So we say that diffraction is a defining test for it. If upon passing that unknown thing through an aperture, it experiences a diffraction, or it gives us results which are like diffraction, we say that object is supposed to be a wave. I'll give you an example. Now, this is going to get a little confusing for you because it is confusing. Imagine I have two slits here. I mean, I have a cardboard and there are two little holes in it. And we bombard this with a lot of electrons. And on the screen, we try to observe it. We can predict that here, right in front of the hole, we will be observing a lot of electrons, right? We will be observing majority of the electrons right in front of the aperture. But if this size was comparable to the wavelength of an electron, how stupid is that? How can an electron have a wave? Because electrons, in our knowledge, it is a particle. This is what you would discuss in A2. Every particle can behave like a wave given the necessary conditions. If you provide it with the conditions that it needs, it will behave like a wave. How will it behave like a wave? How do you know? How do we know how a wave behaves? This is how a wave behaves. Upon passing through an aperture, the waves are seen to be diffracting in all direction. So if you identify something unknown, we don't know if it's a wave or a particle, if it starts showing us diffraction, we will say this particle or this object is behaving like a wave. But let's not get ahead of ourselves right now. Let's try to just keep it simple and discuss only the waves that we know are waves. For example, like water waves, they will show us diffraction. Like sound will also show us diffraction. Like light waves, they will also show us reflection. Diffraction. All kinds of waves, which are waves to the best of our knowledge, they will show us diffraction. But the only necessary condition is that the wavelength, the lambda, has to be comparable to the size of an aperture. Just to give you a perspective, I'll give you a wavelength of light. Let's say the wavelength of light is 650 nanometers. If I want the light waves to show me diffraction, I need to have an aperture that has a wavelength almost approximately equal to 650 nanometers. That means the aperture needs to have a size which will be almost comparable or almost equal to the wavelength of light. Let's say if sound has a wavelength of 30 centimeter, the aperture for the sound to show diffraction, it needs to be approximately equals to 30 centimeter as well. Otherwise, if it is too big, the sound will not be diffracted. If it is too small, sound won't be able to pass through it. Similar is for water waves. Water waves generally, they can have huge wavelengths, but let's say if it has a wavelength of 15 centimeter, the aperture through which it will show me diffraction, that has to be approximately equal to 15 centimeter. The aperture can be slightly larger or slightly smaller, it doesn't matter, but it should not be very big as compared to the wavelength, or the aperture should not be very small as compared to the wavelength. Otherwise, diffraction will not be observable for us. Okay, are you with me so far? Great. Now, going back to our discussion about the Young's double slit experiment. Okay, this is going to be slightly more advanced as compared to what you have studied so far about diffraction. Okay, so let's say I have a light source. All right, this is a light source. Of course, this light source is giving me a wavelength. I just remembered what exactly is a monochromatic light source. Monochromatic, for 1 mark. What does monochromatic means? Mono means single, and chromatic means frequency or wavelength. So if I say a wave is monochromatic, that means that wave only has a single frequency and the frequency is not changing. I'm going to define it for you. I'm going to try and clean it. Monochromatic would mean a light source or a wave source giving out a single wavelength or single frequency. Here, I'd like to give you an example. Imagine white light. Do you remember that white light has 7 different colors? Red, orange, yellow, green, blue, indigo, and violet. All these 7 colors, when they get together, they form white light. So is white light going to be monochromatic? No, it's not monochromatic. If it is just a single color like red color, it will be monochromatic. If the light is only orange color, it will be monochromatic. If the light is only yellow color, it will be monochromatic. But if it is a combination of different wavelengths, it will not be considered to be monochromatic. Okay, So in my discussion here, I'm saying that this light source is a monochromatic light source. Okay, that means it is emitting a single wavelength in all directions. That means the waves which are traveling everywhere, they're all going to have a single wavelength. Now I'm going to place a barrier in between here in its path, and there's going to be a small aperture here. Okay, this dotted lines that I have shown, this just shows us the diffraction of it, the spreading of wave. The waves are spreading everywhere. Now if there are, instead of one, okay, I like to improve myself. Instead of one hole, I am going to place two holes here, because we are talking about double source interferences. So if there are two holes here, the same light is falling on this first aperture S1 and the second aperture S2. Okay, both these S1 and S2, they will allow light to spread out this way. And now I'm going to place a screen in front of it here. Okay, you need to listen to me very carefully. The sources S1 and S2, they are not actually sources. They are just holes in the cardboard. Hence the name double slit. Double slit. When the light from the source illuminates the double slits start behaving like sources of wave, even though they are not. Even though they are not emitting waves, light waves are coming from this light source. But S1 behaves like a source of light, and S2 will also behave like a source of light. Imagine if there was no screen over here and you were trying to observe it, you will see two very bright holes of light over here in the cardboard. Everything else will be dark. There will be only two very glowing spots, right? So these two, S1 and S2, they will start behaving like two different sources of light. Both the sources will be monochromatic. That means they are going to emit single wavelength and single frequency of light. Okay, now this line that I just erased, I'm going to draw it a little further like this. So when the light form from S1 is spreading out and S2 is spreading out this way, they will, you can see this is going to be a little area where the light coming from S2 will be falling on light coming from S1. All right. In this area, what are we going to observe? Now, whatever I show you, it is going to stay the same. Okay, this is basically an observation. It's considered to be a scientific fact. When you look at this screen where the where the lights are actually meeting, you will see that exactly at the center, right in front of the center of S1 and S2, here you will observe a very bright spot. And on either side of it, you will observe dark spots. And then on either side of it, you will observe bright spots again. And then you will observe dark spots and then bright spots again. This pattern of bright and dark spots that I show you here is called an interference pattern. I will explain to you why this pattern happens, but before that, you have to register that this interference pattern is going to happen here. Why? I'll explain to you. First, we understand that exactly at the center, there will be a bright spot. And on that bright spot, on the either side of that bright spot, there will be dark spots forming. If you ask me why this happens, I can explain why this happens, but this pattern is never going to change. Okay? Yes, go ahead, beta.
Sir, the light source, the wavelength that it's emitting,
Yes.
it's not So it doesn't make any sense how they pass through the slits.
The light that is coming from the source is like this. The light is, have you ever seen a torch light? The torch light
Yes.
kind of gives out light in a spreading outwards direction. So if you place a little hole in front of it with a cardboard with a little hole in it, light will be able to diffract through that hole.
All right, I got it.
Okay. Similarly, if there are two holes, light will diffract through both these holes.
Okay.
Okay. This spreading out that I'm showing you here, I'm going to highlight it with gray. This entire region, the gray part, this is happening because light from S1 is spreading out. You know, like it happens in a projector.
Yeah.
Okay. And similarly here, this part here that I'm showing you with the gray here, this part is going to show you light diffracting from S2. There is going to be a small region where the light from S1 and S2, they are going to fall on top of each other, creating this interference pattern. Do you register the interference pattern?
Sir, it stays like that, like
It will always be like that. Always.
no matter what source we have.
No matter which light source you have, if you have a light source, you're going to see bright spots. If you have a sound source, you're going to hear spots where sound will be higher and sound will be lower. If you have water sources, you will have areas where you will see water being displaced to a maximum position, and then there will be some areas where there will be no displacement of water at all.
All right, all
Okay.
right.
So these
Yeah.
bright and dark spots, they are only for light, but this phenomena is true for water waves and sound waves as well. Okay. But Young's double slit can work with water. It can work with sound. It can work with light. Here I am showing you with light only, but it can work with all types of waves. Are you with me so far?
Yes.
Okay, that is great. I am going to explain to you why bright spots and why dark spots are formed. Okay, right. So wherever you see a bright spot forming, we'll write that down as a note. Wherever you see a bright spot forming, wherever you see a bright spot formed where constructive interference takes place, where constructive interference takes place. Just to recall, what does constructive interference means? That means crest on crest. That means crest of wave coming from one source and crest of a wave coming from another source falls, or trough on trough falls on each other. This is where the bright spots are formed, and they are called bright fringes. This is the scientific terminology for that bright spot. And where a dark spot is formed, dark spots are formed where destructive interference. Do you remember that destructive interference happens when crest of one wave falls on the trough of another wave? Crest falls on trough and vice versa. So here on this diagram, wherever I have drawn a bright spot, that means here the constructive interferences are taking place. And wherever there is a dark spot being formed, I'll use a black color for that, this portion and this portion and this portion. The dark spots are indicating destructive interference. That means at these points, the waves coming from S1 and S2 are interfering destructively. That means the path difference between them will be equal to half of a wavelength. So delta S will be equal to 0.5 lambda or 1.5 lambda or 2.5 lambda and so on. Whereas for
So
bright
could you
spot,
explain this again?
the half a wavelength part,
No, from the start.
the constructive and destructive part,
Yes.
we have discussed this in our earlier lessons that when a crest of one wave and a
No,
crest,
sir, I understand that.
okay, you understand that. Okay, I'll draw a diagram that will clear things out for you. Okay, let's see.
Okay.
Uh, these are the two light sources, and that's the screen that is being formed. And on the screen, we are going to see, I'll show you red spots. So there will be a red spot, then there will be a dark spot in the center, and then there will be bright spots like these. Okay, the red spots are indicating bright spots, and the dark spots are indicating the black spots. So the dark spots, these dark spots are called destructive interference regions, and the red spots are called constructive interference regions. Now, for imagine this central position. Now you got to be attentive here. The wave that is coming from this source, let's call this S1, and the wave coming from S2, when they meet at this point, do you realize that the length of these black arrows is equal? The length, this
Yes.
length and this length, they are going to be equal. So waves coming from S1 and S2, they both have traveled equal distance. So for the central position, the path difference is going to be 0 lambda. Okay. Do you understand
All
that?
right. Yeah, I got it.
If for the destructive interference area, the one that is happening right above it, if you observe that the wave that is coming from S1, it will be traveling slightly a longer distance as compared to S2. These arrows are not equal now because we are
Yeah.
slightly above the central position. Here, the wave that has come from S1 would have traveled a longer distance as compared to S2. And how long is that distance going to be? Delta S will be 0.5 of a wavelength. That means wave from S1 will have traveled half a wavelength more than the wave coming from S2.
Sir, is it like a constant 0.5 or do we have to calculate this?
No, it absolutely has to be a constant. That is exactly why, because this interference pattern is a universal
Oh, okay.
phenomena. It's something that does not change at all. It's like gravity. Okay.
All right.
Now for the one that is occurring right below it, this one here, the delta S has to be 0.5 of a wavelength, but wave coming from S2 will have traveled a longer distance as compared to the wave coming from S1. Do you understand that?
Yes.
Now, I'll give you just one more example and then we'll move on. Okay. From this diagram here, let's talk about this one here. Let's call this point P. The wave that is going to come from S1 till P here, it would have traveled a longer distance. The wave coming from S2 till P would have traveled a shorter distance. So the delta S in this case is going to be equal to 2 lambda, because this one was going to have a path difference of 1 lambda. This black spot was going to have a path difference of 1.5 lambda. Do you see? As we continue to move from the central position to the bright or dark fringe above it, the path difference keeps increasing by half of a wavelength.
Yeah.
I am so glad that you understood it. Now I'm going to involve some mathematics here. Are you with me?
Mathematics for what?
I'm going to show you what mathematics here, what kind of questions are we going to expect from this
Okay, I
question.
thought I was ready to this. All right.
Okay.
I
I'm
got
going
you.
to
Okay.
show you a few lengths. This was the central point. This was the first bright fringe. That's what we call it. The central one is called the central bright fringe, and the one above it is called the first bright fringe, and the
Sir, could you
one
write
below
that?
it is also called the first bright fringe.
All right, could you note that down, please? The names.
Okay. This one is the zero, yeah, central bright fringe. I'll write that down. This one is the central bright fringe, Fringe. This one here is the first bright fringe. Then this one here is the second bright fringe. All right. The one that is below the central one is also called the first bright fringe, but this one lies below the central line. This one will be the second bright fringe as well, but this one will lie underneath the central position. Okay, now I'm going to show you the Young's double slit formula. Young's double slit formula. I'm going to redraw the diagram because the earlier one is getting messier already. I don't want to do any more working on that. These are the two sources, S1 and S2. They are not actually two different sources. They are actually illuminating the screen from the same light source. That means this light source that was monochromatic, that means it gave out a same single wavelength. So the pattern that will be forming on the screen, it's always going to be the same. The one that is in front of this central line is going to be a bright fringe. Then there will be dark fringes on either side. Then there will be a bright fringe here again. Then there will be dark fringes on either side. So the gap between the centers of the two bright fringes here, X is often called fringe separation. Fringe separation, gap between two fringes. It is represented by the variable X. The gap between the slits and the screen, this gap here is going to be represented by a variable D. This D is called the gap between fringes and screen. And there's going to be another length involved here, the gap between the two slits. These two slits will be represented by a variable A. A is called slit separation. I am just defining the variables. I'm just pronouncing them. A will be the slit separation. A will be the fringe separation. D will be the separation between fringes, I like to improve this, between slits and screens, not fringes and screens. Slits and screens. The wavelength that is coming from the source is going to be represented by lambda. According to the Young's double slit formula, all these variables, lambda, A, D, and X, they will be related with this equation. Lambda equal to A times of X divided by D. Lambda equal to AX divided by D, where lambda will be the wavelength. X is the fringe separation. A is the slit separation. And the D is the gap between slits and screen. One can wonder, where did this formula come from? This formula was derived using trigonometry, but we don't have to derive it. This formula is mentioned in our question paper, lambda equal to AX by D. This formula needs to be recalled and used. Recalled and used. So all these 4 variables that I have defined, they are all related by this equation. What type of questions you can expect from it? Examiner might give you different values of A, X, and D and ask you to find out lambda. So all you have to do is just substitute the values in the equations and find out lambda. We take a little break and see if you are with me so far. All right, I'm going to show you a few important relationships that we can make from this equation. Lambda, the entire purpose of this formula is to discuss the fringe separation. Fringe separation, that means we want to see that how can we make bigger or smaller smaller fringe separations. How can we make that? So from this relationship, from this equation, lambda is directly proportional to x. That means if I want a bigger fringe separation, that means if I want the fringes to be more separated, I need to use a bigger wavelength. See, lambda and x, they are both present in numerators, but on opposite side of the equations. That way, lambda and x are both directly proportional to each other. So that means for wider fringes, use larger wavelengths, lambda. The next relationship that we can make is going to be between x and d. X and d. D is directly proportional to x. How do I know D is directly proportional to x? The two variables that we are interested in, x and d, one of them has to be on the other side of the equation. So if you take d on the other side of the equation, it becomes a part of numerator. So x and d, they are both going to be directly proportional. That means if I want bigger fringes, I need to place the screen at a longer distance. So for wider fringes, place screen further away. I'll give you a relatable example about this. If you have seen a projector, if you look at this, if you place the screen closer to the projector, you will see that the screen that is formed on the screen is going to be a smaller image. But if you move the screen away from the projector, the screen keeps getting bigger. That's exactly what is happening here. If you keep increasing the distance between the fringes and the screen, that means you're placing the screen further away from the slits. That's when the fringes are going to become wider and bigger, but they will start getting dull. So I'm writing this down here. Increasing D causes fringes to become dull.
Sir, could you mention the projector example as well? It's really
I
helpful.
will mention the projector example for you. Projector. When screen closer to projector, image is brighter but smaller. And when screen away from projector, when screen is away from projector, image is dull but bigger. This is exactly what happens in case of bright and dark fringes. If you keep the screen closer, the fringes are brighter. If you keep the screen further away, the fringes are dull, less bright, but the size becomes bigger. Are you with me so far?
Yes.
All right, that's great. The third relationship that we can form from this equation here, it's going to be between A and X. A and X. See, if I want a relationship between A and X, A goes on to the other side of the equation and gets divided. That way, A and X, they are going to be inversely proportional with each other. Inversely proportional with each other. So I'm going to write a little description for you. If I want the fringes to be wider, that means I want X to be greater, A has to be smaller. So for wider fringes, keep A smaller. What does A smaller actually means? It simply means slits closer to each other. If you remember from the diagram, that's where I labeled A. A here was the gap between the two slits. If this gap is bigger, the X is going to be smaller. The bright fringes are going to come closer to each other. If this A is smaller, that means the slits are closer. That's when the fringes are going to become further away from each other. That's the third relationship that we can form in this case. Do you understand that?
Could you repeat this again?
Okay, I will show you here on a diagram. Let's say the fringes, the slits are closer, and in another case, the slits are further away from each other. In this case, when the slits are closer, that means the A is going to be smaller, and in this case, the A is going to be larger. So in case when the A is smaller, that's when this is going to be a bright fringe, this is going to be a bright fringe, this is going to be a bright fringe. But in case of A, which is larger, the bright fringes are going to be smaller and they are going to be closer to each other.
All right, I got it.
Smaller A means wider bright fringes, and larger A means closer bright fringes.
So when we say smaller bright fringes,
Yes, you can say closer and smaller bright fringes. Is that all right?
okay. Yes.
This is one of the easier topics from this chapter because they ask you to they will ask you to perform calculations using relationships. They will say what happens if the distance is doubled, what happens to the size of the fringe. If the distance is halved, what happens to the size of the fringe. They can ask you questions like that, or they can give you values for A, X, and D and ask you to find out wavelengths. Okay, these are the only two types of questions they can ask. Is that okay?
Yes.
That's great. We have last few minutes remaining. I'd like to give you an introduction of the next subtopic from the same chapter, and it is called the diffraction grating. Okay, it's just going to be an introduction. I'm not going to go into a lot of details here for today. What exactly is a grating? A grating simply means a piece of glass or plastic having small holes in it. And when I say holes, I mean a lot of them. Okay, when I write the plural holes, I'm talking about a lot of the holes, like around 5 centimeter holes per centimeter. That means a 1 centimeter piece of that glass might have 500 lines on it. These lines are perforations. They are indicating that this line is it's a symbol of a hole. Okay, so if there are 500 lines per centimeter, that means 1 centimeter of that glass plate is going to have 500 lines on it, so close to each other. They are made on it by using machines. We can't manually make those lines. The lines, they behave like holes. You know, the way we discussed it in the previous topic, there were two holes in the cardboard. Here, it's going to be a glass plate that looks like this. And by using a machine, we have scratched these lines on it. Each line will behave like a source of light when I shine a light source on it. Okay.
Okay.
This is how we represent a diffraction grating. You can see I'm leaving a lot of empty spaces here. These empty spaces are indicating a lot of slits, the little holes that we talked about earlier. So there will be a light source coming from these slits. And on the screen, we are going to observe the same interference pattern again. There will be a bright spot, then there will be a dark spot on either side. There will be a bright spot, then there will be a dark spot on either side. In case of diffraction grating, we call these to be, you were going to say something?
Yeah, I was gonna say, so the slits, basically the holes, they're the same size, right?
Yeah, they are the same size, and their size is supposed to be comparable to the wavelength. Okay.
Okay.
All the slits, they are supposed to be of the same size. Of course, I'm drawing it freehand. That's why it looks a little different. But
No,
the
no, it's just
sizes are same. Okay.
all right.
The bright fringes formed on the screen in case of diffraction grating are called maximas, and the dark spots are called minimas. Minimas. Why? Because minima is formed where destructive interference takes place, and a maxima is formed where constructive interference takes place. Okay, these are just different names. Otherwise, they are the same bright and dark fringes that we discussed earlier.
Yeah, I was gonna say that.
Okay.
Okay.
All right. This is where I'm going to stop our lesson for today. This was an introduction of the next subtopics. I'll give you a quick revision in the next lesson, and then this is where we'll continue from. Okay.
Okay.